Hello, class. So on this video, we'll continue talking about what we were talking in the previous videos, where we're talking about the roots of the characteristic polynomial. Right? So I define, when we start with this function, y equals e to the rx, we plug it into this homogeneous ODE, second order, with constant coefficients. And this polynomial that we get, this polynomial of r, is what we call the characteristic polynomial. So I said that in the previous video. Now we saw that the solutions that we get are going to depend on, well, three cases, right? Either this characteristic polynomial has two real distinct roots, in which case we did all the work, and we saw that our general solution is given by this equation here, and that it works for all real numbers. Right? So this is the general solution for on the interval negative infinity to infinity. However, we also saw that the problem cases were going to be where we had one real root, multiplicity 2, and two roots with imaginary components to it. So we took care of case 1, where we have two real distinct roots in the previous video. So now let's see the second case, when we have one real root of multiplicity 2. So again, we're working with the characteristic polynomial, P of r equals AR squared plus BR plus C. We're looking for its roots. Right. So when does this polynomial have one real root of multiplicity 2? Well, so we have a formula for, so I'm not going to write R1 and R2 in this case right now, right? But we know by the quadratic formula that the two roots have this form. So I'm just going to write it like this. So when do we only get one solution out of this expression? Well, for us to get only one solution out of this expression is equivalent, right? So R, or this expression having only one solution, let me write the whole thing. And again, this is multiplicity 2 for the one solution. It's equivalent to b squared being equal to 4ac. Why is this the case? Well, if b squared equals 4ac, then what happens when we look at r? We get r equals negative b plus or minus the square root of b squared. It's the same as 4ac. So we get 4ac minus 4ac over 2a. Right? Well, 4ac minus 4ac is 0. Right? So we get only minus b over 2a. And that is our only root. And it has multiplicity 2. So again, this characteristic polynomial, or in general, any quadratic polynomial having only one distinct real root with multiplicity 2 is equivalent to the term inside the square root, which in our case is b squared minus 4ac, or for what's inside the square root, let me say it like this, to satisfy that b squared equals 4ac. Why? Because that makes whatever's inside the square root be equal to 0, and we get our only root, multiplicity 2, to be negative b over 2a. So that's bad. Why? Because we want a fundamental set of solutions. So at least we want two solutions, right? Then we need to check that they're linearly independent, but in this case, we don't even get two solutions. We only get one solution, y1 equals e to the rx, which is e to the negative b over 2a. So how do we find a second solution? We're kind of stuck. Well, there's actually a way to find a second solution. I'm not going to prove it, but I'm going to show you how to do it. Okay? And that's this next theorem. And this works more generally. This doesn't only work with second order homogeneous ODE. It could be that the coefficients of the differential equation also have coefficients which involve the independent variable. So this is going to be more general, but we're going to use it for the case in which we only have constant coefficients. So let's read what the theorem says. So this theorem is called the reduction of order theorem. Let me try to underline that a little bit better. So the reduction of order theorem. Suppose you have a second order homogeneous ODE. Again, we're not requiring for the coefficients to be constants. So let me make a note of that. Right, so they could be expressions involving also the independent variable. So the coefficients don't have to be necessarily, I think I still misspelled it. They could involve the independent variable or include. Let's write it like that instead of involve. So they could include the independent variable. Which in this case is x, right? So it's more general, but again, we're going to use it for the case where we have specifically constant coefficients, right? So suppose you have a second order homogeneous ODE. It has this general form, right? There's at the start, if there's something multiplying the y double prime, just divide by that, right? So I kind of skipped some steps here, but in general, it always has this form. And suppose that there exists a solution y1, right, to this differential equation, which I'm labeling as 2. Suppose that there is a solution defined on I. And in fact, I want to make it more specific, not only defined on I, but with interval, because I already introduced this notation. I don't think I had done it before. In my previous class, with interval of definition, right, being I. So remember that for the interval of definition, it's more than it just being defined, right? There could be other things that restrict what the interval could be, right? So just to make it more general, not only define an I, but with interval of definition equal to I. Right? Then we can actually find a second solution on I, which has an interval of definition equal to I as well. And that second solution is given by this messy expression here. Y2 equals Y1, and I'm writing of X here. I could have ignored it, but I'm writing of X. So the second solution is given by Y1 times the integral of e to the negative p to the x, e to the negative integral of p of x dx divided by y1 squared dx. So the integral of that whole quantity. Right? So what the theorem is saying is that this y2 defined like this is another solution to the differential equation on the same interval of definition. And in fact, y1 and y2 are going to be linearly independent on this interval I, meaning that they're going to form a fundamental set of solutions. So again, I'm not proving this. I believe that they prove it in the book. It might be section 3.3 where they do this, or 3.4, not exactly sure. But if you look in the book, in either section 3.1 or 3.2, they prove that this is in fact a solution with the same interval of definition as y1, and that y1 and y2 are linearly independent on this interval. Now, in the previous class that I taught, or the previous time I taught ODE, or applied differential equations 1, I actually had the students go ahead and show all this, so basically prove that this is true. In this case, since they struggled a little bit, I'm not going to have you do that. I will have you use this theorem in the homeworks, right, in future homeworks. But I won't ask you to prove it. Again, if you want to see a proof, look back in the book in either section 3.3 or 3.4. So what matters for us is that we can use this to find a second solution to the differential equation we were looking at, or we're looking at right now. Why? Because we already know what one solution is. We know that one solution is e to the rx. We can use this theorem here to find, or this expression to find the other solution. And they're going to be linearly independent on whatever interval of definition the original solution had. Okay. So let's go back here. Actually, I'm going to do it in another side. So we were looking at this this polynomial equation. We found that we had the real solution. So I'm not going to write everything again, but we had one unique solution of multiplicity 2. So had one real solution. Of multiplicity 2 given by r equals negative b over 2a, right? What that meant for us is that we had one solution where r is given as above, and I don't know if I wrote the x here. Yeah, see, I forgot to write the x there. So we have one solution, right, e to the negative b over 2ax, right? But since we're working with a second order homogeneous ODE, we can use the reduction of order theorem to find another solution. First, let's find what the interval of definition is for this particular solution, y1. So note the interval of definition for y1 is all real numbers. Why? Well, let's check the things that we have to check for the interval of definition. Y1 is definitely defined everywhere, right? Its domain is all real numbers. It's just an exponential function. And in terms of the ODE, remember that the ODE is ay double prime plus by prime plus c equals 0. There are no restrictions on x that come from this differential equation. Right? We're not taking the square root of x. We're not dividing by x. So really, there's no restrictions on this function. So the interval of definition is, in fact, negative infinity to infinity. Now, what that tells us is when we use theorem 1 to find the other solution, whatever other solution we find is also going to have interval of definition being negative infinity to infinity. And these two solutions are going to be linearly independent on this interval, negative infinity to infinity. Okay. So let me just write that. And then in another video, we're going to actually go through the work. By theorem 2, or by theorem 1, sorry, the solution y2 that we find will also have this interval of definition. And again, I'm not proving it, but they're also going to be linearly independent on this interval. That's again just from the theorem. Meaning that they will form a fundamental set of solutions. Right? So all that is left for us to do to find the general solution is use theorem 1 to find y2.